Today, I just want to give you a bit of a global view on use of structural steel for tall buildings. I think India, as you know, is going through a rapid growth. I think we forget, and the world forgets, that over the next 20, 30, 40 years, there's going to be 500 million people in India urbanising. 500 million people. Whether we like it or not, it's a fact of life. And I think that's going to open our eyes. We really do need to progress quickly in terms of use of material, technology, in terms of developing tall buildings. But I think today, I'd like to just talk a little bit about what's happening around the world, and hopefully it sets the scene for what we are going to be expecting to be challenged with. So just some facts about on tall buildings around the world. CTBUH, Council for Tall Buildings and Urban Habitat, is sort of the official organisation that tells us what's happening around the world about tall buildings. And there's been some very, very strong trends over the last 70 years. When you think about 70, 80 years ago, 90% of the 100 tallest buildings were in the US or North America. And I'd say about 80% of those were in Chicago and New York, two cities. Now, or maybe 1 or 2 years ago, 80 to 90% of the 100 tallest buildings in the world are in Asia and Middle East. And in India, India's going to be in the picture. At the moment, it's China. In the next 20, 30 years, India's going to be in there. So that's one trend. Second trend is that the 100 tallest buildings in the world 70, 80 years ago were office buildings. Now, it's the other way around. 70, 80% of the buildings are mixed use and residential. So that's an important trend. And with the urbanisation that I was talking about, that's an important fact for India. And the third one is 70, 80 years ago, the buildings were essentially structural steel, the tallest building, the tall buildings. Now, it's concrete and composite. Okay? Now, why? When you think about concrete, I come from Australia, originally from New Zealand. The strength of concrete in Australia, readily available, is 140 megapascals, cube strength. 140 megapascals. That's one trend. Steel is steel. Okay, we've got high strength steel, but the concrete is 4 or 5 times stronger. And the second big development is advanced formwork systems. And if you look at a tall building, these days you can build a floor every 3 to 4 days. And the core, or the central core, probably 2 floors every 5 days. And so it's fast. And hence, steel has a bit of a battle. Now, I know we're going to be talking about structural steel, but all I'm saying from my experience globally, that for residential towers that are reasonably standard, tall towers, concrete is going to be the answer. But probably the better answer is composite. But let's just stick to concrete. So why steel? Why is there a healthy future for steel? Well, I want to show you some examples where steel is the answer. So characteristics of a tall building, well, speed of construction. When you look at a tall building, for 80 to 90% of the total time to build a building, 80% of it, the critical activity is structure. So the faster that you build the structure, in other words, floor cycle time, and the earlier you start the structure, means that you're going to finish the building faster. And for tall buildings, that's very, very important, because you've got huge holding costs, and the quicker you build the building, the cheaper it is. And so we think in terms of steel being a faster construction material, and I think that's one of the big advantages. So there's a huge amount of savings to be made. The second most important thing about tall buildings is that the taller you are, the taller you go, the cost per square foot is going to be more costlier. And it's quite quite dramatic. As you get to 70, 80, 90, 100 stories, the cost per square foot is significantly more compared with your 20, 30-story building. So the way we think should be a little bit differently. There's going to be a lot higher holding costs, so speed of construction is going to be important, huge loads, so the size of our columns are going to be very important. Lots of speakers have talked about smaller columns, hence higher FSI, hence higher returns, and so that all comes into the picture. So that's something that we get to keep in back of our minds in terms of cost per unit area. So I want to talk about, just show you some of the projects that are happening around the world from BuroHappold, where structural steel has been the answer. And you'll see that, you see where we really do need to use steel, and concrete's not the answer and structural steel is the answer. So this is a pretty impressive project. It's called City of Dreams. It's a hotel in Macau near Hong Kong, where it's a composite construction. You see on the right-hand side where you've got the steel skeletal frame, and steel is the only solution for this because of its randomness, its geometrical form. But we still got concrete slabs, composite concrete slabs, so it's concrete and steel. We've got a conventional reinforced concrete core, and we've got interior steel columns. A very, very complex project, very complex geometry. Obviously, steel is the only answer for that perimeter frame. Very, very expensive, but I forgot to tell you, why is it so complex? Because the developer is willing to pay the money for it. Why is he for a hotel? Why? Because I forgot to tell you that in there, just in the basement there, is a casino. And casino makes a hell of a lot of money. And that's funding that hotel. And the people that win are going to live in that hotel. The people that lose will probably go to another cheaper hotel. But that's going to fund that project. And I think people forget that at the end, whatever material we use, there has to be a cost effective. There has to be a return. And hence the reason why this is a complex project, because the developer is willing to fund it. Because the return is going to be high, because there are people that are willing to stay in that hotel, and the casino is also funding it. And so it's free advertising. That's very, very important. Sorry, I've gone the other way. So how does a poor old structural engineer design this? It has to be designed. So technology has to move with these complex structures. You can't do it the conventional way. So we're interfacing software like Rhino and using Grasshopper to transfer geometry that the architect dreams. He comes up with a form because they've got the computer to come up with a geometrical form. 10 years ago, the architects were they had software that can provide geometrical form, but the structural engineers and the contractors did not know how to define the geometry. And us engineers, we need geometry to feed into our analysis packages. But now, that can be all done automatically. So in one go, from architect to a structural model, we can do all this with the software that we've got available to us. And so with the workflow and BIM capabilities that we have now, we can go right from beginning, from architects and engineers. We can get the geometry. From the geometry, we can get straight into the analytical model. From analytical model, we can get into design, because it's all digitized, and we can get straight into production of drawings. And it's only possible now, in the last few years, that we can do all this sort of stuff. Previously, it's almost impossible. Then, of course, the complex connection designs. The structure is only as good as its weakest link, and in India and a lot of countries, in terms of doing complex structures, we have our weakness in terms of connection design. That's the important part of a structural steel design. So now we can automate all this with BIM. And so I'm just going to give you a bit of an example here. So this particular project, you get from the geometry, right from the geometry you can identify connections, and you know what members are coming into that connection, and so you can focus on the connections, identify all the identical connections so we don't have to repeat the design 4 times, and then using Grasshopper we can create our own final element meshes. So just have a bit of a look. It's all automated. So locally you get into a finite element model and out comes the answers, and get into a post-processor to do the design. This whole process for the whole building, it's a question of just hours, as long as you configure it correctly. So if the architects decide to change something, it can all be automated. And that's where we're heading. And that's why we can do complex projects, and that's why we can make use of structural steel to do complex projects. It's almost impossible to use reinforced concrete. And so I'm just going to show you some images for this particular project. We talked about use of structural steel and what are the weaknesses, and obviously the finishing is very, very important for a structure like this, and the paint work, the fabrication finishing, it's very, very important. The process is very, very important, and that's something that I think India is going to get better and better at. Well, we have to get better and better at it if we want to make use of structural steel. The design life of these buildings have to be comparable to reinforced concrete if we want to make use of structural steel. You can just see some of the complexities associated with this particular project. But it's only through advanced technology that we can use structural steel and create buildings like this. Very, very complex. Okay, the next one is National Bank of Kuwait, in Kuwait. Another building which is quite iconic. Why? I want to go back to that image. Why are we doing this? Why is the client building such a complex building? Obviously, the cost of that building is going to be very, very expensive. But it's the National Bank of Kuwait. It's the world headquarters, and so being a world headquarters, it's free advertising. The owner is prepared to pay maybe double the cost, because the return in terms of marketing through just the iconic nature of their headquarters will pay the returns. And so there is a developer that's willing to spend the money. It's not an architect's and engineer's dream, it's the developer's dream, because they're prepared to pay the money. And we can't forget about that. We shouldn't forget about that. So a very complex building. For the engineers, they'll appreciate that this building, because it's asymmetrical, the centre of mass is separated by quite a large distance compared to the centre of stiffness. So the building wants to tilt over. And if it's in reinforced concrete, it will continue to tilt over because of creep. But steel doesn't creep. And so steel is a good material to stop that building from continuing to tilt over with time. And so we're trying to constrain to minimise the movement, long-term movement. And the other obvious reason why it's structural steel in the perimeter frame is because of its complexity. And so that was the driving force in terms of why we got steel. Because there's a curvature on the facade, there are strut tie actions, and of course the other big difference that I know it's obvious, but when you start having strut tie actions, concrete can't take tension, so we need steel. Sure, we can have reinforcement, etc., but it's quite complex, and so steel is the answer. So because this building is going to tilt over, the facade is curved, there are tie forces and there are compression forces in the slab. And so the answer for our floor system was a composite floor system, not only for steel beams to support the slab, but the steel beams in the floor system to take the strut and tie forces generated by the curvature of the building. You can see some of the complexities associated with the shape of the building. So not only was this floor system, as I said before, just to take the slab loadings, but you can see that because the columns and the perimeter are curved, you need something to tie the columns back to the core to prevent the columns from pulling out. And so the green core, or the whole building, wants to keep tilting over, and so we needed to have this system of structural steel and outriggers to stop it from falling over. And so it's very, very complex. You can see the perimeter frame connected to the green core by those outriggers. Very, very complex. You look at the picture, the amount of fabrication that's involved, it's fairly complex. So that sort of brings another topic, that in India, the use of structural steel, it's all about the whole process. In terms of in India, we've got the challenge of getting the infrastructure. We need infrastructure to get from the fabrication shop to the site. We need craneage. And with all the technology we have, the infrastructure, steel is very competitive because it's time. Steel is the answer in terms of reducing time. The material cost might be a bit more expensive, but time is even more beneficial in terms of the bottom line cost. So there's just some of the latest pictures, just taken I think last month. You can see the building's progressing quite rapidly. Lots of structural steel, but it's a pretty, you couldn't do this in concrete, otherwise it would be just all concrete and no glazing. The forces are huge because of the permanent load that's trying to, exerts lateral loads into this building. This is one of the projects that I was involved in Sydney back in the 1980s, and there's a different reason why this building had lots of structural steel, quite different reasons. First of all, this project went through in the 1980s, initially started off as an office building, but then they decided to make it a residential building, and then back to office building, and at the end it became a residential building. The interest rates in Australia were 15 to 17%, the funding, right? So this building, regardless of what it was going to be, had to be built quickly. And so the reason why it was structural steel adopted was because using structural steel enabled us to have 3 construction fronts. And I can't get the pointer to go, but by using structural steel, what we were allowed to do was get these steel tube columns up to the first floor that you see at the top there, and that was your standard apartment floor. So we wanted to get there as quick as possible, right? We wanted to get the core up as quick as possible. And so you got 4 construction fronts there. You got the core, you got a workforce that's rapidly just moving ahead, and you want to get that done as quick as possible so they can install the lifts in there. And so the lifts then can mobilize the labor force to build the floors. We can get the standard floors to shoot up, so that's the second construction front. The third one is to do all this complex ground floor podium levels, very, very complicating. There's markets, retail, lots of different usages. And so that took a long time to build each of those floors. And the fourth one is down in the basement. So what it meant was that we had 4 construction fronts. So by the time the apartment floors were to level 40, the rest of the building will be finished as well. So it would be all finished in one go with the 4 construction fronts. So the whole project was completed in less than 2 years, because even though it had a lot of complexity in it, and it was only possible because of the use of structural steel. And this was the first time in Australia where we used concrete-filled steel tube construction, which is another, well, we can talk about it for hours. Okay, nearly finished. Sure. And so we all used to the floor system, basically a composite floor system, steel beams, steel decking, pour the reinforcement concrete, Now this sort of system is rapidly being used in India, and I can see lots of use for this in India, even in a conventional concrete building. And so that's another topic that we can talk about. So just since I'm giving a bit of a world perspective and global trends, some of you might be familiar with the buildings, some of you may not be, but there's been some fantastic applications of structural steel in tall buildings. Obviously this building, I don't like talking about it too much, but it's the World Towers. I mean, that was the first structural steel towers that were pure structural steel. Even the core was structural steel. But we know the unfortunate events. My friend Leslie Robertson, the designer, and he gave me lots of lectures on the project itself. But that was a good example. Of course, the Empire State Building, you all know, it doesn't look like a structural steel building. It looks like a solid concrete or masonry building, but it is a structural steel building. And people forget that this was 80 years ago, or 70 years ago, 100 stories built in 13 months. Right? This building was completed in less than 1.5 years, 70 years ago. And so, yes, there is hope for structural steel. And the comment that I am going to make is that in India, where structural steel is going to be used is modular high-rise buildings. We are going to be building future 70, 80, 90-story buildings that are affordable for the masses, and it's all going to be built in a factory. That's going to happen in India. It's going to happen. Maybe 10 years' time, 20 years' time, but it's going to happen if we're going to use structural steel. But that's the future, and that's a good example on why structural steel is a huge advantage, can be used. My other favourite building is Bank of China building. That was 20, 30 years ago, designed by I.M. Pei, and Leslie Robertson was the engineer for this. It was courageous. It was a courageous building. It's probably an expensive building, but it is the headquarters for Bank of China. And so it's not a developer, it's Bank of China, who want to make a statement to the rest of the world that we are the best bank in the world. And if they're going to be the best bank in the world, they have to have a damn good looking building. And so they were prepared to spend the money. A fantastic example of structural engineering, architecture, and an owner that's prepared to pay a little bit more money. But this particular building, because of its skeleton, a bit like a transmission tower, all the load, in fact, 90% of the load goes to the four corners of the building. And so there is no central core, it's all suspended, just like a transmission tower. But a fantastic example. And my other favourite building, the Hong Kong and Shanghai Bank in Hong Kong. This is also a steel building. What a fantastic example, just to fulfill an open space in here. Open space in here because the Funchu and the Chinese community, they want the spirits, the evil spirits, to pass through the building, and so they needed an open space there, and that's why this building was conceived. And what a fantastic example of structural steel, where all the loads go to there and there just by conventional truss, bit like a bridge, and you can see this central column getting heavier as you go up because it's in tension and it's not in compression, so maximum load at the top. But what a great example. But why? It was an expensive building. It was going to be the headquarters for the biggest bank in the world. So there was a reason. CCTV in Beijing. Once again, China want to make a statement, defeats gravity, structural steel is the answer. So, I think steel is going to be the material to satisfy the demands of China and India. Maybe not this year, maybe not next year, but certainly in the next 10 to 20 years. Because in these two countries, we've got the urbanisation, and we are investing money. You can see people are investing money in the steel. And we're going to have a huge demand. I think there were some figures, tonnages that were floating around in the last session. Well, that's just going to exponentially grow to to match the appetite of the 500 million people that are going to move into cities. So, thank you.